Okay. Can you all see the screen?
Yes.
Okay. Thank you. So let me get started. So this talk is going to not be slide heavy. So the first thing I want to tell you all is the slides are largely for me because I forget what I need to say. So the slides are there for me to remember what to say, not for you to mostly read. There are some pictures which are very relevant for you to see, but when you see a slide with a lot of words like this, don't worry about it. It's just mostly for my benefit. You can just listen to what I'm saying and look at the pictures, right? So, okay, so what is it about today? We are going to talk about the inverse square law and what are we going to learn, right? Like what we are going to talk about and what we are going to learn are different things. What we are going to learn is to discover hidden similarities between things that are very different, and as a second step, explore where those similarities end and why exactly. You know, what is common, what is not common, and why are things common and why are things not common. So I'll periodically pause for questions, but at other times, at any time, if you have a question, please ask away on chat, and either me or Janani will look at it and take your question at the right time. When I pause for questions, please feel free to unmute yourself and ask any question you have in mind. We did this poll. That's great. I in the poll I saw that there are some younger kids in this session. So some of these topics require some basic concepts that are not yet covered in, let's say, a fifth grade or a sixth grade, but that's okay. Don't worry about that. So what I have done is, if a slide requires some concept that is not yet covered in, let's say, fifth or sixth grade, I have put a picture, an owl picture. The point of having this picture is to point out that there is something new that you're seeing, and to not worry about it if you're not understanding it too much, because I've made sure that even if you don't understand the actual things that you haven't yet seen in school, you at least get the overall story, right? So watch out for this owl picture for some of these advanced topics, and pay close attention there. It's great if you can get it, but no worries if you don't get everything, right? And yep. All right. So the first question is this, right? Does the intensity of a force reduce with distance? I hope most of you understand the terms here. The intensity is the strength. Do you think the strength of a force reduces as you go further away from where you are? Okay, I see some comments. Largely everyone agrees that it does reduce. That is great. And yes, it does reduce with distance. And this is probably something that you can relate to. Yep, Tejas correctly points out that it is inversely proportional to the square of the distance, hence the inverse square law, which we will be getting to. So if any of you did not have an intuition for force reducing with distance, if your mama or papa are yelling at your ear, it sounds very intense, but if they're yelling from some distance away, it's fine, right? Like we find it easier to ignore it if they're yelling from the next room. So the force does reduce with distance. Now, the cool thing is that qualitatively, meaning as a description, we know that it reduces with distance. And like Tejas said, some of us know that how exactly it reduces. But for the others, right? It is useful to predict how this force reduces, right? Like you are at some place and then the sound or light or something is at some distance. It is very useful to determine how the force reduces as you go away from the source of the sound or light or whatever, because it helps us answer very practical questions, right? Like, for example, if there is going to be a concert and you are responsible for stage design, right? Like, how do you know how many lights are enough? You've put on some spotlights. Do we need more or do we need less? Is this going to be too much, too less? Wi-Fi, right? I'm sure all of us have experienced this thing that sometimes Wi-Fi is not strong enough at all places in the house, right? So when we put a router, do we, at home we probably don't do this, but let's say in a more professional environment, we are designing a network. We would want to think, okay, how many routers are needed? How much spacing will this be enough, right? Also, maybe some of you have heard of this term called slingshot in context of space, right? Where when we launch a rocket, we don't launch it directly. We launch it towards the moon or some other planet, and then it goes and does a U-turn around that and uses the gravity to accelerate towards the final destination, right? So things like that. For example, will the rocket actually crash into the planet, or will it go around and get slingshotted? So having a formula to predict this is really useful for things like this. And now we hit the first slightly advanced slide for the younger kids. There is this owl picture at the bottom right, so please pay attention. This is the formula for predicting the force of gravity, right? Don't worry about it if you have not seen this before. Just understand that capital G is a constant, and M1 and M2 are the weights of the masses, and R is the distance between them. This is the force of electrostatic attraction or repulsion between two charged particles. Again, don't worry if you have not seen this formula before. Just know that K is a constant, some constant number. Q1 and Q2 are the charges, the strength of the charges, and R is the distance between them. Likewise, for light and sound, the intensity at some distance is the power of the source divided by 4 pi x squared. Again, don't worry if you don't know 4 pi, it's some constant times the distance squared. So these are the formulas for some bunch of different forces. So now I want to pause and ask you something. Do you notice something common? Go ahead and let me know what you think on chat. Let's wait for a few seconds. Is there something common that you see here? Some pattern? Let me know on chat. Correct. All the formulas have plus sign. Yes. F is inversely proportional to the distance. Yes, correct. Distance. Janini is stress testing the question by saying equal to is common across all formulas, which is 100% true. Equal to is there everywhere. But I think a few of you have noticed. Let me call out the commonalities. So for example, all of them have a constant, right? So there is some constant here. Yes, they all have variables. That is correct. So they all have a constant, and they all have variables which measure some magnitude, either mass or charge or power or something on the numerator. And they all have the distance in the denominator as a square. Right, correct. So there are a lot of things that are common across these. And honestly, if you ask me, each commonality is probably worth sit down and a discussion for half an hour to understand why they are common. The context of today's talk is the fact that all of these have distance squared in the denominator. So r squared, x squared, right? So before we jump into this thing, I wanted to take a few minutes and especially for the younger participants, give them a sense for what x squared and x cube are. right? I'm sure all of us know this formula. X squared means x multiplied by itself. So 2 squared is 2 times 2, 4. 15 squared is 15 times 15, which is a bad example because I think it's 225. I had to recollect that, right? So x squared is the number multiplied by itself. X cube is the number multiplied by itself one more time. So this is the mathematical formula, but what do they actually feel like, right? How does a x squared look like? How does an x squared taste like? How does an x squared feel like, right? And how do they grow in relation to other things? So I wanted to give that intuition. Take a few minutes. So this is going to be pictorial. Now, for the next few minutes, I want all of you to look at the screen because there are going to be pictures, right? So I have X here. Please follow my laser pointer. I have X here drawn visually as a line of some 1 unit, right? It could be 1 centimeter, 1 inch, something, right? 1 unit. And x squared, if x is a line, then an x squared is essentially a square of the same, with the side as the same size as x, correct? Because x squared, what is the area of a square? It is side squared, right? Like this is the area, the green area is x squared. So if x is this much green, then x squared is actually this much green. So it's not just 2 times or 3 times, it's a lot more, correct? And an x cube is as much green as a cube of side x, right? Now, this is, let's say, side 1. Now, watch how it grows, right? Now, when from 1, if we go to 2, right, x takes 2 steps forward, right? X takes 1 step forward, so it becomes 2, length 2. But x squared, notice how x squared went from 1 tile to 4 tiles, right? X went from 1 to 2, but x squared went from 1 to 4, right? So it went up by a much bigger step. And x cube went from 1 box to 8 boxes, right? That's huge. Now for, right, how about 3? For a size 3, for x, see, it went just 1 more step, but x squared went from 4 boxes to 9 boxes, and x cube went huge, right? Now I'm just going to quickly scroll so that you get a visual idea for how they grow, right? Look at how x grows as a line, but look at how x squared grows. X squared grows really fast, and then x cube just explodes, right? It's occupying my entire slide. So I hope you get an intuition for how these things are growing. Here is another way to see the same thing, right? Whatever I had drawn, I have put as numbers here. So the first column is x, the second column is x squared, and the third column is x cubed. Now, these are the values for x and x squared, right? Like, for example, for if x is 2, 2 times 2 is 4, x squared is 4, x cube is 2 times 2, which is 8. If you take 5, x is 5, x squared is 5 times 5, 25. This is not 126, this is 125. Sorry, there is a typo there. I will fix this, right? Now, let's say x squared and x cube are three people in a running race, right? Imagine how the race is going to look like. The first step, x takes 1 step, x squared takes 1 step, x cube takes 1 step. That is fine. The second step, x goes 1 step ahead, but x squared has gone much further and x cube has gone way ahead. But imagine what happens, right? Like at the end of 6 steps, poor x has gone only 6 steps. X squared has gone 36 steps and x cube has gone 216 steps, right? So x is like the tortoise and x squared is kind of like the hare, but luckily this time it is not the hare that sleeps before the finish line. It is the hare that just keeps bounding. And if x and x squared are the tortoise and the hare, then x cube is more a rocket, right? It's not like x squared is a fast tortoise. X squared is a different animal. And x cube is not even an animal. It's just a rocket, right? Okay, so then this is just a different way of showing the same thing. For folks that are more comfortable seeing the graphical representation, this is probably some of the elder kids who are used to seeing graphical representations. X is a linear line, x squared curves up and accelerates, x cubed accelerates way faster than that. I do want to call out that I have done something shady with the whole x-axis and y-axis. If you notice, even though the graph is a square, x-axis is only 10 and y-axis is 100. Because x squared and x cube are so fast that if I have a x-axis also as 100, then line x will be going like this, but x squared and x cube, you won't even see the curve. They will just shoot up like this. So I had to do some shady business to even show you the difference in the curves, right? Right. Now I just want to show you the same picture with the whole intuition for tortoise, hare, and rocket. If you are comfortable with the algebraic expression of x, x squared, and x cube, stick to that. If you have not seen that before, if these have not been taught in school before, remember this, right? The tortoise goes slowly, the hare goes fast, and then the rocket just explodes, right? So this is what we have seen now. Now I want to take one conceptual jump ahead, right? So if we are talking about x, x squared, and x cube increases, the speed of increase. But if you put them in the denominator, the same thing happens, but it is about the decrease rather than the increase, right? 1 by x decreases slowly, 1 by x squared decreases very fast, 1 by x cube decreases super fast. In no time at all, it will be nothing, right? I hope you have understood that. If x squared and x cube are on the numerator and they talk about increases, 1 by x squared, 1 by x cube are on the denominator and they talk about decreases. But essentially, they are relatively very different in terms of speeds, right? So that is a important intuition that I want you to take away from this session. And let's apply that to this, back to this picture, right? Where we saw the square in the denominator, we saw the square of the distance, right? R is the distance, R and X are the distances. So the idea is that, if you remember the first question I asked you at the start, is that as you go further away from the source, you feel the lesser of the force. And all of you agreed with me that it is lesser. But it is lesser like a rabbit. It is not lesser like a tortoise. It becomes lesser very fast. So, for example, I mean, yes, your mama or your papa shouting from the next room is much lesser than them shouting near you. But even if they took one step behind, right? Like they are shouting very close to you, even if they took 2 steps behind, the intensity reduces by a big margin. Notice how square changes, right? It goes from 1 to 4 to 9 to 16. Since you put it on the denominator, it reduces in that speed, right? So you get a big reduction in force, even with a small increase in distance. So obviously, this is a very, I'm trying to explain the feel of this whole thing, right? So this is not mathematically precise. In your higher grades, you will get the mathematical precision, but for now, understand the intuition behind it, right? Even if you take a few steps further away from the source, the reduction in force is really big. So for example, like we discussed, someone shouting in your ear, or even not talking normally in your ear, and talking normally from this much distance is a big difference. For the children that are aware of gravity and gravity at different planets, right? The gravity at Mercury is much greater than that of Earth. It's not just twice or thrice or whatever. It is much greater because it is that much closer to the sun. So the gravity, as you go closer, increases like a rabbit. It increases with the square of the distance, right? A flashlight is much brighter. I hope you all have had the opportunity to, after your lights off, use a flashlight and read under covers in your bed. It's a great, fun thing to do. I don't know if you have noticed, if you turn on your flashlight and when you're reading with the book right next to you, the flashlight looks very bright. But the same flashlight in the room does not look that bright, right? So That is the first step, right? The fact that as you move away from the force, the intensity reduces very rapidly. Now let's go back to that formula that I showed you, right? Gravity, light, sound, electrostatic force, so many different forces that are fundamentally very different physical phenomena. They all seem to reduce the same way. They all seem to reduce by x squared, by distance squared as you move away from them. Now let's pause for a minute and appreciate that the curiousness of that thing. You know, gravity is fundamentally a very different force from light or sound, right? And electrostatic force is very different. So what's going on, right? Like, do you all find it surprising that they all seem to reduce the same way? Go ahead and share some thoughts on chat. Do you find it surprising? Do you not find it surprising? Why do you find it not surprising? I'd like to hear some thoughts here. Any thoughts? Do you guys find it surprising that gravity and light both seem to behave similarly? Did you expect this? Right, on different planets. Yes. Uh, Confused, Matthew. I hope you're confused in a good way. I hope the rest of the session answers it. But if you are confused about the question itself, my question is that this, right? Like, if you see, everything has a r squared and an x squared in the denominator, but these are all very different forces, right? Gravity is very different from electrostatic force, and sound is very different. So how come fundamentally different phenomena have the same behavior? So I can tell you, I'm glad that some people are not surprised. Yes, Tejas says not surprised as all forces have some inherent similar properties. Yes, it will be great if Tejas, you could also tell us what it is that you think is similar, because that is very close to the topic of the of this session. Right. So please continue to share your thoughts. I am very curious to hear the thoughts of the folks that are saying not surprising. So if you think, no, if you think that, oh, speed of gravity, oh my God, this is scary. This is a scary topic. I am, I am just about qualified enough to recognize that this is a scary topic that I have no idea of. I have no hopes of doing justice to. But speed of gravity is something that you should talk to some folks, some really good physics teachers about. So Mahi, hold on to that thought and bring it up with Utpal sir, or I don't know, one of the physics pros. Right. So folks that said not surprising, please share some reasons. I will get back to the slide for now and then look at the chat later. So I was personally initially very surprised because honestly, all through school, I was thinking of all these forces as separate because they were separate chapters. I mean, I know it sounds very hilarious, but yeah, sometimes some of us are really silly in ways we don't realize, right? So I was thinking, okay, gravity, light, they're all very different. And because of that, I was very surprised when they all seem to behave the same way. And then sitting and thinking about it helped me understand what is similar. And that's what I want to share with you today. So before we go there, uh, let's take a simpler example, right? Before we talk about big things like gravity and light and all. Let's take something very easy and very manageable. So here is a water droplet falling on a surface. So this is in slow motion. And as the droplet hits, right? As the droplet hits, the ripples are spreading outwards, right? I hope you can see that. Now, the question that I want to ask you is, look at the height of the ripple, because the ripple is basically the force, right? The water droplets force is spreading outwards, and visually you can see that force as a ripple. So the force reduction you can see as the height of the ripple, correct? So look at the height of the ripple. We all know that force reduces as you go away from the source. So the source is here. As you go away from that, the force is reducing, the energy decreases, correct? Now, the question that I want to ask you all is, how does it decrease? Does it decrease like a tortoise or like a hare or like a rocket, right? So just to help you answer this question, when someone is speaking in your ear, and if they go a little bit further, the force decreases by a large margin. So the question that I'm asking you is, from where the water droplet is landing, as you go further out, is the ripple height becoming smaller slowly, or like a rabbit, or like a tortoise? So get on to chat. I see a bunch of interesting answers already. Let's give folks a few more, a minute to think about this. If any of you did not understand the question, just let me know on chat and I can try to restate it in a different way to make it clear. So let's say the height of the ripple at this point, watch my cursor, right? The height of the ripple here, there. From there to the height of the ripple here. Does it reduce like the tortoise graph I showed you, or the hare graph I showed you, or the rocket graph I showed you? Hmm. Okay, a few people seem to think that it is like a rocket, because if it is a rocket, then it should stop almost here itself, no? If the force is reducing so rapidly, then very soon it should be nothing, no? So I think my personal opinion is that it reduces, like, initially, like someone said, it starts off like, because of the rebound and all of that, it looks like a hair. But then if you see the slightly outside, it reduces slowly. It reduces like a tortoise. So initially there is some confusion going on because of the whole bounce and all of that. But if you see this area, see, largely the ripple is the same height. It slowly reduces and diffuses. So this is more like a tortoise. So I have tried to draw this picture from a drone cam, a drone shot of it, right? Like you're looking at it top down. This blue dot is the ripple. And when the ripple falls, the force spreads in all directions evenly. And as the force spreads, it causes a ripple, and the blue line is the ripple. Correct? I hope you understand. This is basically the same picture that I've drawn here as a top-down drone shot. Now, if you have not realized already, I am not very good at drawing. This is the best I can do. I'm sure all of you all are really good, but I've never been that good. So let's say this is me standing here, or this is you standing here, and you are able to hold a cup, right? This yellow thing is a cup. So let's say you can cup the ripple. How much force, how much of the original force would you feel in your hand if you held your hand like this, right? So let's, whatever the original force is, how much of that original force will hit your hand, this golden area, as against how much of it, what part of it will go away. So the answer is that half of the original force will hit your hand, correct? Because you are cupping half the bubble. So half of the original force will come and touch your hand, and the other half of the force will not touch your hand and go away. Correct? Now, let's say my cup is like this. So get on to chat and tell me how much of the force will I feel? So let me repeat the question. If I cup my hand like this, I feel half of the force. If I cup my hand like this, how much would I feel? Oh, I missed a lot of the answers. Sorry. Yes, I see a lot of folks have said quarter. Great. There is some interesting answers that says less than half. Matthew says all. That is surprising. Are you pulling my leg, Matthew? So, if you cupped your hand only this much, you would feel quarter of it. If you had a different answer, I'm very curious to hear what you thought. But let's go with quarter for now. Now, generalizing that, right? The force that you feel is the ratio of the cup size to the overall perimeter of the bubble. So for the younger kids, I'm referring to it as the perimeter of the bubble, which is the blue circle here. The older kids will know of this as the circumference of the circle, correct? So if this is half and if this is quarter, then the generalization of this expression is that the force you feel is the ratio of the cup size to the circumference of the circle, right? If you have just 1/8 of the cup circumference as your cup size, you will feel 1/8, correct? Now, this is for the slightly older kids. Give it a shot. Instead of a cup, let me say I am standing here at a point in the circumference. So I have given you a clue already that the blue is the circumference and yellow is a point. So what fraction of the force will I feel at this point? Ooh, 1 by 360 is an excellent guess. I love that. Anant, you should pursue that. You should pursue that line of thought. Yes. So Tejas, Tanay have got the right answer. I think Dave wanted to type it, but maybe hit enter a little bit too soon. But Anant, your answer is fascinating. You should think more about that. That's a great answer. 1 by 360 is not something I had thought of. Uh, I want to take just a few seconds to address that 1 by 360 answer. Now the thing is, even 1 by 360 is not quite a point, because you know if if the whole if the whole angle is 360, then a quarter will be 90. So 90 by 360 is 1 by 4, and the half will be 180. So 180 by 360 is 1 by 2. All of that is fine. But when you say 1 by 360, it makes a small v here. You understand? It's like cutting a small slice of pizza, but it is still a slice, right? A point takes it to a even more smaller thing, right? So yeah, the thought process is brilliant. I really appreciate that. You should think more on that, and as you hit, I don't know, uh, trigonometry or whatever, you should try to relate the whole 1 by 360 thought process to how it ends up being 1 by 6.28 r or 1 by 2 pi r or whatever the correct answer is, right? So yes, the right answer is it is 1 by 2 pi r. So what I've done here is grayed out the circle and the forces and the whole circumference and all of that. It is the same picture. Notice it is the same picture, but the points of interest, stay with me here. The truly interesting bits are where is the source and at what distance you are from the source, correct? So if I were to generalize this, even without thinking about circles and all of that, if I just know the source and the distance from it, I know that the force I'm going to get it is maybe 1 by 2 pi r times the original force or something like that, right? Now coming back to the original picture, the ripple subsides more gradually compared to someone talking near your ear versus 2 steps away, because the force of the ripple is spreading over this 2 pi r circles, right? It's spreading over this larger and larger 2 pi r circles, right? So the ripple, the reason why I picked the ripple, let me tell you 2 things. Let me tell you why I picked the ripple, and let me tell you why I said ignore the drop, the place where the drop bounces. One of you was very smart in telling that first it looks like a hare and then it looks like a rabbit. I had not realized it. Thank you. I learned something from you today. That is 100% correct. The reason is that I chose a ripple because it is an approximation of a 2-dimensional space as against a 3-dimensional space. So in 3-dimensional space, you have length, you have height, width, and depth, right? So there is height, there is width, and there is depth. But in a 2-dimensional space, you only have length and breadth, only 2 things. Now, the problem is the reason why it looks like a hair initially is because initially it is actually a 3-dimensional thing, because the bubble is bouncing, right? So it decays rapidly, but then soon it approximates to a 2-dimensional space. And that's why it starts looking like a hare and then becomes a tortoise. So big clap to the person who spotted that. I'm sorry, I did not catch the name, but great job. So cool. So now now that we have looked at a 2D space, the obvious fun next thing to do is to look at 3D, right? Like what happens in a 3-dimensional space. So again, a question for you all. In a 2-dimensional space, a force spreading will look like a ripple, right? It will look like circles that are growing outwards. In a 3-dimensional space, what would it look like? So get on to chat, give me ideas. And by now, I'm really curious to hear what you all think, because I've gotten some fascinating answers. Okay, Mega says sphere, RJJ says sphere. Nice. What other answers? Yep. Nice. A lot of you have said sphere. I was hoping someone would say something interesting like a balloon or a bubble or something, but yeah, you're right. Essentially, it spreads in a sphere, correct? So if this is the source of the energy, just like how in a 2D space it spreads like a ripple, in a 3-dimensional space, it's going to spread like a bubble, right? It's going to spread like a sphere because it is going in all directions equally, right? Now, I think by now you all know what I'm going to ask you next. Let us say that you are standing here. So my famous diagram strikes again, my famous stickman strikes again. Let's say you are standing here at a point on the sphere. What fraction of the original force would you feel? So I think I should have put a whole picture here, but even the younger kids, if you have been with me till now, take a guess. What fraction of the overall force would you feel here? I'm not looking for formulas. If you know formulas, that's great, but I'm looking for some intuition. So get on chat and describe in your own words. If initial force was 10, let's say some units, right? And I am a guy standing at some place in the sphere. on the top or here, wherever, what fraction of the original force would I feel here? You know, we asked the same question with the bubble, right? So let me quickly scroll back and show you the question in the bubble. So the question that we asked is, if I am a person standing here at the tip of a bubble of a circle, what force would I feel? What fraction of the force would I feel? And the correct answer was 1 by circumference. Same question I'm asking you here. What fraction of the force would I feel? Getting good answers now. By 2r cube by 8. Okay. 1 by 4, 3 pi r cubed, 1 by 2 pi r, 1 by 4 pi r squared, 1 by 4, 1 by 4 by 3 pi r cube. Ah, okay. Interesting. Okay. So half of total surface area. That is if I cup half the bubble. Mega, your answer is correct for my first question, where I said if I cup half, how much I would get. So if I cupped half the bubble, I would get half of the total surface area. But let's say I just have a point, right? I see some folks have gotten it, some folks are working through it. I think Dave is thinking that it is 1 by volume, whereas many others have said 1 by surface area. Dave, that's something that you want to pause a little bit and think about. Should it be 1 by volume or should it be 1 by surface area? It's an interesting thought. Yep, I kind of guessed you meant surface area but put the wrong question. Yes. So, yep, the answer is, as most of you got it, the force is evenly spread through the surface area, and any point that is some distance away receives 1 by surface area of the force, correct? The force, so here is an owl pick for the kids that don't know. The force at distance r is 4 pi r squared. That is the formula. You will get to it, I think, in 6th grade or 7th grade, depending on your syllabus, school, whatever. Eventually, even 7th graders might be getting to it later in the academic year. But 4 pi r squared is the formula for the surface area of a sphere. Ooh, some people are getting to it at 10th grade. Wow. So lucky you guys or unlucky you guys, I don't know, but you've learned it now. So 4 pi r squared is the surface area of a sphere, and the force at distance r is 1 by 4 pi r squared. So now let's think about this. We keep talking about this fancy term called pi, right? For the ones that don't know, the value of pi is basically 22 divided by 7, right? So that's it. Pi is just a symbol for 22 divided by 7. So that evaluates to 3.141, whatever. Yeah. So you can, if you don't know what pi is, I don't want to scar you with an improper understanding. So I'm not going to try to explain it. Think of it as a number, right? It is a letter for a number. That's it. It is number which is slightly more than 3. Okay. So 4 is a constant. 4 is always 4. Pi is always slightly more than 3. But r changes with the distance. So for 3-dimensional space, the force that you feel, someone has posted a long answer for pi. Some point in the distant past, I remembered the 10 digits, but Ishan seems to know much more than that. Pretty cool. So yeah. So the general way to state this is that in a 3-dimensional space, the force that you feel is inversely proportional to the square of the distance, right? So you remember the formula that I showed you, where I asked you what is common for all these formulas, and you saw the r squared at the bottom, x squared at the bottom. This is where it comes from, right? So now try to connect the dots here. The reason why gravity, light, sound, electrostatic force, the reason why all of them follow the inverse square law, this is called the inverse square law because this is a square of the distance and it is in the denominator, so it's an inverse, right? The force is inversely proportional to the square of the distance, so that's why it's called the inverse square law. So think about recollect the formula where I drew those little red circles for the r squared in the denominator, right? The reason why all these different forces follow the inverse square law is because they all dissipate like bubbles, right? In whether it is a small point, an LED, small LED that is emitting light, or a small buzzer that is emitting sound, or a point mass that is attracting, that has some mass and has a gravitational pull, or it could be an electrostatic charge. Whatever it is, that force is spreading from the source in a bubble in three-dimensional space. And that is why the formula is common. So going back to the question that I asked you initially, what is it that is common about all these forces? The fun part is it is not the forces themselves that are similar. The forces are very different. What is similar is that they are all operating in a three-dimensional space and they are all spreading in a three-dimensional space. And in a three-dimensional space, they spread as a sphere and the force is spread across the surface area of the sphere. And that is where you get this inverse square law, right? The force is inversely proportional to the square of the distance. This is the statement of the inverse square law. Now, this is not new. This is Johannes Kepler. Some of you might know his name already. Very famous scientist from the 1600s, right? In 1600, I think it was 1604 or something, if I remember. So here is a screen grab from Wikipedia, right? Kepler wrote about light, the intensity of light, way back, 500 years back. Notice this. I think Kepler has described this much more beautifully than any of us can. What he's saying is there is as much light in the smaller sphere as it is in the wider. So the smaller sphere is more dense and compressed than the larger sphere. So let me show you the picture, right? So initially when the sound came, first the sound was in this dark red bubble. Then it slowly spread to the light red. Then it went to the orange. Then it went to the yellow. What Kepler is saying is the amount of energy is the same, but as it spreads, the energy spreads across a bigger thing. Oh, wow. Great comparison. Like the Big Bang. Yes. I had not thought of that. That's a really cool comparison. And I will go back and think about whether it truly is like the Big Bang. I am not able to tell you right away, but it feels very appropriate that it should be like the Big Bang. So yeah, I always go by different people think through things differently. I start with a feeling and then try to poke at it and think whether this feeling is correct. Is there data to substantiate it and so on? So Anant, what you say feels correct to me, but I can't, I'll have to think more to really truly understand that. But yes, essentially it is the same energy that is spreading. So when I explain this, I think of the balloon, right? Like all of us have blown balloons. If you think about it, the amount of rubber material, the balloon material, right? Red balloon, the red material in the red balloon, the amount of material is the same, just that it spreads over a different area, over a greater and greater area, and it spreads evenly, right? So if you think about it, Kepler is essentially saying that. He's saying that there is as much light in the narrower surface as it is in the wider, just that the narrower one is more compressed and dense than the wider one, which is more sparse. So this is just I wanted to share this with you because when I saw this quote, I was surprised that 500 years back, humanity was, humans were thinking at this level and they were able to say things like this. Right. So this is the inverse square law. The formula has the same structure because the force is spread in three-dimensional space in the same way. So is that it? So is that it? Nope. That is not it. This is only half of the fun. You remember I told you that we are going to learn two things, right? We are going to try and analyze and discover what is that thing that is common, but there is also a lot of fun in discovering places where it no longer holds. So I quickly wanted to show you a few examples where the forces violate the inverse square law. So there are lots of examples, but I wanted to take a couple of examples and just talk through that. But before I go to that, does someone want to take a stab at guessing some places where the inverse square law is violated? Think about sound, light, gravity, various forces that we have spoken about. Are there places where instead of a hair dissipation, you suddenly see a tortoise dissipation? Is there some place where something is unexpectedly loud for the distance or unexpectedly? Yes, 2D. Ooh, Brownian motion. Yes. In you're right, Anant. In dimensions that are very, very small, often you see that the inverse square law breaks down. Now, but I think that would probably be too advanced for this session. But you're right. Yes, intermolecular forces, Mahi. Yes. So at those distances, the whole sometimes the inverse square law no longer holds. What about more relatable examples in day-to-day life? So don't think in terms of physics or textbooks or whatever. In your life, when you see things around you, are there examples where you see that forces don't reduce as you expect? Nice. Madhvanti says echo. That's a great, great example. Hold on to that thought, Madhvanti. Doppler effect. Interesting. Yes. Okay. Nuclear force. I personally don't know enough about nuclear force to answer that. Car accelerating is a interesting thing. Did you mean something like the Doppler effect there, Anand? This could mean a lot of things. So let me know in chat what exactly you meant by car accelerating. That's a very interesting thing. Yes, molecular interactions. So I want to share a couple of examples that are not as technical as you all are at, but fun nevertheless. So have I really hope you all have had the pleasure of playing with agarbatti tubes. So, but I don't see them around that much. When I was a kid, my parents used to buy agarbatti sticks, and they used to come in a cardboard tube with a plastic cover wrapping. So I used to wait for my mom to buy that, and I used to collect these cardboard tubes and connect them together, and my brother and I would play a lot with that. Has anyone played with cardboard tubes or plastic tubes, PVC tubes? Yep, it's a great toy. I mean, do not underestimate the power of a simple physical object. So much can be done with that. Yes, I am so glad to see some folks have had the pleasure of playing with a tube. So you would realize, I mean, I'm sure you would have played this game where one person speaks into a tube and it feels like a microphone, right? Like if you speak into a tube like this, suddenly your voice seems very loud. And yeah, exactly. Your sister thinks she would be a singer, and she probably sings into the tube, and then it sounds like the voice is very loud, as if she's singing into a microphone. Or the other thing is when one person is having the tube to their ear. Yes, nailed it, Anand. I'm going to get there, right? When one person is speaking through the tube and one person is having the tube in their ear, the sound sounds much louder than if they are just talking, right? What is going on is that the inverse square law no longer holds in the sound energy dissipation through a tube. The reason is that from my mouth, when I'm speaking now, right? Like I'm sitting in a room, the sound is expanding like a sphere from my mouth, right? Like it's expanding like a bubble. But the moment you put a tube and you speak through a tube, all the sound that was supposed to go behind, up, above, everything is focused. Like Anand said, everything is focused into the tube. So the sound does not really spread in a 3D bubble anymore. You're squeezing everything into a pipe. So it no longer behaves in an inverse square law, right? So then now this question should be really easy for you. When your parents are driving you around or when you're going in a bus or something at night, have you noticed how the headlights are very glaring, right? Like they really hit your eye. But those bulbs are very small, right? They are not that powerful. So if you just saw the bulb, it might not, if the bulb was just hanging from a wall, it might not glare so much. But a headlight is very glaring. So somehow the inverse square law is violated here because the energy is coming right into you and it is not dissipating in the square of distance. So it is the same answer again. Basically, there is a curved mirror. If you have seen this picture already, yes, correct. So there is a glass. Oh, there it is not because of the glass in front of the bulb, Ishan. It is because of the mirror behind it, right? The glass in front is just to protect the things inside. But if you next time you go to a car or a bike, look closely, there is a bulb, and then behind the bulb, there is a mirror. And the mirror is not a flat mirror, like Mahi is pointing out, there is a mirror and it is a curved mirror. And the curvature is such that if you place the bulb at the right place, all the light that gets reflected goes straight, right? It goes straight out. So this is what happens. So this is basically, if you keep a bulb here, then it's like a focused beam. And that's how, if you've seen the Batman movies, the bat sign that gets flashed up in the sky. I always used to think, how in the world can the sign go so high that Batman in his tower can still see the sign? And then I realized that they also use a beam, right? They use a large mirror and focus the light so that it gets, the light is thrown to a longer distance. And that is why in this instance also it does not follow the inverse square law. Now consider Wi-Fi. So let's say you are 20 steps away from the router in the same room versus 20 steps away from the router, but in a different room. The Wi-Fi signal in a different room will be weaker if you have thought about it. What is going on? The reason is that, exactly, walls block waves. That is correct, right? So there is some absorption happening, there is some reflection happening, and the Wi-Fi signal can penetrate walls. It's not like it is going to be a 100% block, but there is some absorption happening. Some of the energy gets bounced back, right? So because of that, the signal strength reduces when it goes through a wall. I think generally people say that 3 walls is what a Wi-Fi signal can. It's a heuristic. A Wi-Fi signal is good enough for 3 walls. Beyond 3 walls, you can no longer rely on a Wi-Fi signal. You need a repeater or something like that, right? So in the previous examples, we saw that it was no longer following the inverse square law, but it was stronger, right? The energy was dissipating slower than the inverse square law. In this case, the energy is dissipating faster than inverse square, right? Because of absorption, reflection. So I have a couple more slides, but I basically wanted to pause for folks to kind of, absorb what we have spoken about till now. If there is something that you want to share with your friends, share with me, ask, take a moment, collect your thoughts, see if you truly understood this. This is a good time for you to go off mute and speak also. You can also continue chatting. That's also there.
Karthik, would you want to switch off your screen share maybe?
Yep.
The discussion.
How do I do that? Yes, stop share. So let's take maybe 10 minutes for chatter, and then we can continue back.
Does anyone have any questions or thoughts or something they wanted to share? Ishan, what did you mean by saying your sister thinks she would be a singer?
Using those like cubes, the sound would be in one focus, right? So my sister thinks she would be like a singer, like using a microphone.
I have done that too.
So there's an interesting comment that Anant left when you were asking people where this law would break down. He said maybe a car accelerating. Curious if you had a response to that, Karthik.
I wanted to hear from Anant on what he meant by that. It's a very interesting point.
I thought maybe like when the car is going faster, there's more force being like applied on the road while it's like going faster.
Which force are you talking about, Anant? As in
Kinetic energy and kinetic force.
okay. Okay. So there, in that case, you're burning a fuel, right?
Yeah.
So there is a different force that is essentially making your car accelerate.
Yeah.
That's a interesting point. Okay. It doesn't have to be a question. So if you noticed my slide, let me show my slide. I have said thoughts because it could be thoughts, right? So the folks that were, for example, the folks that were not surprised earlier when I said, is this common, right? What was your thought? And did that thought process change after hearing, after sitting through this session?
I'm curious if we can invite Tejas to respond to that. I could see that he's one of the people who are not surprised, right? Tejas?
Yes, could you please repeat? I couldn't hear you. My speaker had touched.
Oops. Tejas, I was just asking for your reactions because I think initially you were one of the ones that said you weren't surprised that different forces happened to behave the same way. Was this the reason that you were not surprised, or you had a different thought because of which you were expecting this to happen? Or what are your thoughts there?
My thought was very simple that like all forces have inherent properties, so I thought that all of them would be inversely proportional to the square of the distance, just due to their very like nature.
Okay. And now, whatever we discussed, do you think that is in line with what you were thinking, or have you changed your thought now?
No, I had never thought of like the spherical angle to it, like the geometry behind it, but now I understand.
Yeah, that's true. Even I had not thought of applying a geometric perspective to a force, right? But I don't know. I really liked the way of thinking this way. So, how about someone else?
I have a question.
Yep, good.
I'd ask that the speed of gravity is almost same as the light. So if the square is same, then the speed of gravity can be same as the light, right?
I'm sorry. Could you repeat that question, Mahi?
The speed of I mentioned that the speed of gravity may be same as a light. So is that right?
What do you mean by the speed of gravity?
Now,
The acceleration due to gravity, or
no,
something else?
there was this one thing in the part where I had to say that they're not surprising. There was one thing related to gravity. I forgot that question.
So the question was that the force of the gravitational force reduces. But
I
when you
think
say,
it's same.
uh-huh,
I don't remember there was one question actually over there that something happens with gravity and something happens with light,
correct,
but though they are different forces, they reduce by the same amount.
correct.
So it basically means that the speed is same, and even the square was done 2 times for light also, and like the
Yes,
distance for light was also 2, and the speed of gravity was also 2.
yes. So
R2. It is
yeah,
same, right?
I understood. I understood your question. Yes, it is r squared. So when you say r2, you say the way you say it is r squared, and you're right. Your intuition about your intuition in calling it the speed is actually very good. But actually, the right term for it is not speed, because generally when you say speed, everyone thinks about the rate of change of position, right? Like my hand is changing position from here to here in 1 second, so the speed of my hand is this. But then if I change from here to here in half a second, the speed of my hand is more. So when you say speed, people usually think about a physical thing moving, but what you are actually trying to say is that the rate of reduction of the
Yeah,
force is the same.
yeah,
So it is not the speed of gravity that is changing. Actually, it is the rate at which the gravitational force is reducing, right? And the rate at which it is reducing, you're right, it is the same at which the brightness of light reduces, or it is the same rate at which the loudness of a sound reduces. So the brightness of a light and the loudness of a sound are different things, correct? So brightness and loudness are not the same, but if you think in technical terms, they are basically the strength of force of something. So that strength could be brightness of for light. You could think of it as brightness. Essentially, it is the light energy or the sound energy or the gravitational energy, right?
basically
But
if the strength is same, then the rate of reduction of any energy would be same.
yes, provided they are dissipating like a bubble in
Yeah, like it,
three-dimensional space. Correct. You're absolutely right.
I feel like your point was well learned there, Karthik.
Yeah, I'm very, very happy. I'm really happy that Mahi got the idea, but was just lacking the words, the vocabulary for it. Right? This is the best kind of learning where you understand the idea and you just have to put words and say, this idea, it's just called this. Right?
I have
And
a question actually. Sorry, you were saying something.
I just wanted to call out call out the child because she was not hesitant to say that, right? Like that is something that took me a long time to learn. So it is fine. It is fine if you are using the wrong words for it. It is fine if you're using if you don't know the right term for it. It's great that you ask, because then someone can just fill in those little blanks. So you should do more of it. All of you should do more of it. That's great. Sorry, Jenny, you're saying?
I have a couple of blanks actually for you to fill.
Yep.
So I'm curious, the topic that we discussed today, of how force reduces with a distance. I was thinking through this when Mahi asked her question, which was, this is different from the speed at which light and sound hits you. For example, everybody would probably know that when there is lightning and thunder, it will come at, you can time the difference between when you hear when you see the lightning and when you can hear the thunder, and you can know how far away the storm is. But that is different from what we're talking about here, right? We're not talking about we're talking about the dissipation of force and not distance from
Hmm.
you sensing the source of that
Hmm.
force.
When you sense it, right?
Yeah,
How much you sense it is what we talk about, not when we sense it. Yes.
yeah. So
So
no, I was curious if you could expand on that.
yeah, that's an important point. I mean, light travels the fastest, and like someone said, gravity has no speed. Now, that statement, I realized that I need to go learn some more about gravity having speed or no speed. But yes, I a simple level, it sounds like gravity has no speed is a reasonable statement to make. Sound travels, I don't know if you all do this. Sound, the speed of sound. Does anyone know the speed of sound? You want to post it on chat? Come on, 10, 9, 8, 7, 6, 1200 watt. 330 meters per second. So, speed of light is 3 into 10 power 8 meters per second. The speed of sound, okay, 1200 kilometers per hour. So so 343, 330, these are all good answers. Let's try to do a fun little thought experiment here. 330 meters per second is basically, or 340 meters per second is roughly 1000 meters per 3 seconds, correct? And 1000 meters is 1 kilometer. So essentially sound travels 1 kilometer in 3 seconds. So when I see lightning and thunder, it's like, since childhood, I have this instinctive habit of, the moment I see lightning, I go 1001, 1002, 1003, 1004. And then I hear that. And then, okay, it took 6 seconds for the thunder to reach me. So it is 2 kilometers away, right? So it's a quick little heuristic that you can do. If you count the seconds between the lightning and thunder and divide by 3, that is how many kilometers the lightning actually, how many kilometers away at. But anyway, that was a digression from Janani's question, right? That was a fun digression, but yeah. So we've spoken about, let's take lightning, right? We have spoken about how much of the force reaches us, how much of the light reaches us, how much of the sound reaches us. We have not spoken about when it reaches us, right? Obviously, different forces, different energies travel at different speeds. The lightning and thunder is a brilliant example. Thanks for that, Janani, because the both of them happen at the same time, but then they travel at different speeds and reaches at different times. So we are explicitly not talking about the speed at which they travel, right? We are only talking about the intensity, the dissipation of the energy. Okay. All right. So is there one last comment that someone wants to squeeze in? Go on unmute and speak up, or post something on chat. Take a cue from Mahi and not hesitate and ask something, because you might think it is silly, but it might end up being a brilliant point like what Mahi made. Okay, I'll give you some time to, is someone unmuting? Did someone unmute? Oh, okay. Okay, so post something on chat. Let me get back to the slides. I just have a couple more slides to cover. Okay, so I had some of these bonus slides, which I think we will not have the time to get to, but I will just briefly mention this so that if you're interested, you can go back and think about it. There is something called the sonic boom, right? The sonic boom is a very loud boom that you hear when aircraft crosses the speed of 1 minute. Sorry, my speaker is announcing reminders. Sorry about that. It's asking me to drink water. So yeah. So coming back, sonic boom, right? Like a sonic boom is when an aircraft crosses the speed of sound, right? Like the sound travels at 1 kilometer every 3 seconds. If an aircraft is traveling slower than 1 kilometer every 3 seconds and then accelerates past that threshold, it causes a boom which can rattle windows. It can even break glass. It's really loud. So if you think about it, the aircraft is up in the sky. The regular engine sound, the regular plane sound, everything, the sound of it tearing through air, all of that you hear normally. But then the sonic boom, the intensity is much louder. So this is one of those very, very interesting places where the inverse square law is violated, because our glass does not break because of regular planes, but it can break when there is a sonic boom. So I don't want to get into the details here, but for the ones that are interested, please read what a sonic boom is. And the reason why it no longer adheres to a inverse square law is because the energy of a sonic boom is not spreading in a bubble like this. So you see how the bubble is drawn as circles here, right? But during a sonic boom, the energy is focused in a cone. So this is called a Mach cone, and the energy gets focused in this. So obviously, since it is very similar to a beam, right? Like the headlight example we saw and the pipe example we saw. There is something interesting happening because of which the energy gets focused. We don't have the time to get into that, but very interesting if you guys if you have some time. Here is another interesting thing that I quickly want to talk about. So this is two magnets, right? They are at standstill and they're very close, but they accelerate so much by the time they come into contact that they break this glass. They just shatter this glass. The speed that they gain is just so much. Now look at this. Look at this another example of a magnet. This metal thing is the magnet. It moves closer by a small bit. It does not move closer by a large bit. So here the star is as it is, but just a little bit closer, and the whole thing falls apart and comes and sticks together, right? So as you can see in both these examples, it is no longer the hair. This is like a rocket, right? The force is increasing way more than just x squared when you come close. So this is like a rocket. This is no longer like a hair. So why is magnetism different? So I just want to give you some hints so that you can go and read more about it. In all the other examples we spoke, we implicitly assumed that it was a point source, a bulb, a speaker, a water droplet. But with a magnet, there are two poles. There is a north pole and a south pole. There are 2 points of energy source. There isn't a single point. So that is a fundamental assumption that no longer holds with magnetism. I'm talking about a traditional magnet like the pictures that I showed you. Now, what happens? Why is that important? The reason it is important is that when you have a north pole and a south pole, at some distance away, the attraction of one pole starts getting cancelled out with the other poles forces, right? Like essentially the north and south poles forces start cancelling each other out. And the force is no longer a sphere. It is no longer a bubble. I'm sure some of the older kids would have seen that picture, right? That iron filings experiment where you put iron filings and place a magnet beneath and it forms those ovals, right? I forgot to put a picture, but you must have seen those oval picture and then the lines out. So the force is not spreading in a simple spherical field. The force lines are much stronger near the poles. So because the force is no longer spreading in a bubble, the inverse square law no longer holds, and there are some of these other things. The thing that from this section, the thing that I wanted you all to take away is that real world is messy, right? So someone told me about an echo. Someone told me about focusing. Madhuvanti told me about an echo, right? So in the real world, it's not just a perfect place where you have a point source and then forces spread nicely in spheres. There is focusing happening, there is absorption happening like Wi-Fi, there is reflection happening like echo, there is scattering happening. For example, in fog, right? If you have headlights in fog, they are not that effective because light scatters more. There is interaction with other forces. There are corner cases. But the point is, that is where it is. That is where the fun is, because right, like understanding something is fun, but these are like puzzles. Okay, it should be like this, but it is not like this. Something else is going on. What is that? So it's really, there is a lot of fun in solving that puzzle. So some more food for thought. In 2D space, we saw that it was a bubble. I mean, it was a ripple, and it was inverse to distance. in 3D space, it was a bubble and it is inverse to distance squared. What about n-dimensional space? Right? In a 4-dimensional space, for example, would it be a inverse cube law that applies instead of an inverse square law? In a 5-dimensional space, would it be the inverse 4th power law that applies by default? Is that something that we can generalize? So think about it. If you are very interested in knowing more about this, I'm just going to post a name called, so this is the name of a scientist called Gauss, right? So there is this scientist actually generalized this. So there is a nth dimensional generalization for this. You can read about it. In fact, you can ask ChatGPT to explain it to you. It will do a great job. There are there are lots of other places where this shows up. I picked 3 or 4 examples for consistency. Size perception, right? Objects that are far away seem smaller than objects that are close, but the rate at which they grow smaller is like a hair. It is no longer like a tortoise. As it comes closer, it becomes bigger and bigger very fast, right? So size perception follows kind of like an inverse square law. One of our faculty, Ashish Kulkarni, the economics teacher, he was telling me that the gravity model, there is a gravity model of international trade. When countries trade with each other, apparently researchers have modeled that along gravity, and apparently they've had inverse square laws applied to trade. So it's really cool. And we are just a couple of minutes over time. So this is the last slide that I had. So we initially thought we will learn why many phenomena have similar equations, right? But that was a fake. That was not the goal of this session. That was just the vehicle. So the true message that I hope you all understand and take away is that if you take the effort to truly understand something, right? I think it was Tejas who said that. I don't know who it was. One of you told me that they never thought of applying geometry to this and thinking in geometrical space what happens, right? But it's magical to truly understand what makes something tick, what is happening, right? And the second thing is places, once you've found a pattern, places where the patterns break are almost always interesting. They might sound frustrating because you might have worked very hard to find a pattern, and then it might be very frustrating to find that, oh, this pattern holds for this much, and then so till 1 2 3 4 it holds, but for 5 it doesn't hold. That is not a reason to be discouraged. That is actually, it's almost like a treasure map, right? It is trying to tell you something, that there is something that one has not understood, or there is something more complex at play, because of which the pattern is breaking at some point. So, yep, with that, I think we are done.
Wonderful. Thank you, Karthik.
Thank you.
Karthik spent many hours designing this class for us and even more thinking through this. And so thank you for taking the effort and the time. I'd love to hear from you all. Did you feel like you learned something interesting in today's session? Yeah. That's a big yes, Karthik.
Really glad to see that.
Wonderful. Superb.
Great. And
Lots of yeses.
yes. Thanks a lot for sticking through a long session, and thank you, Janani, for helping me out with this deck. Really much appreciated. So much from you.
So folks, I'm hoping I see you on further masterclasses. I've posted the link to the next one in the chat, and there's a lot more scheduled, so you can go take a look at the Gifted World website. Masterclasses are always free and are always as interesting. So I'm looking forward to seeing you again. Thanks, Karthik.
Thank you. Nice seeing you all. Bye.